do with the molar mass. We have equal mass, we have equal volume. Okay, so in this case, equal mass divided by, say if you have 50 grams of everything, both things there, 50 grams divided by 28, 50 grams divided by 40, well, the smaller number in the denominator means a higher number of moles. So in this case, we know this is a true statement there. So there are more nitrogen molecules than argon atoms there, because the atomic mass for argon is higher than the molar mass of nitrogen gas. If you have equal masses there, you're dividing the same number by a smaller number, you get more number of moles. More moles means more particles. Okay, so that's the true statement. And it has nothing to do with the kinetic molecular theory there, but this is a prelude of the next question. The other questions there will use that information. More molecules in the same volume means a more crowded situation, so that they are going to fight with one another more frequently. That's the last statement there. Okay? So the second statement says the pressure is greater in the argon class. Well, is that the case? PV equals to nRT. So we can actually use the ideal gas law to figure out the relationship between the number of moles and the pressure. So PV equals nRT. If you rearrange that equation there, P equals to nRT over V. Now we have the same temperature, same volume, so RT over V is the same for both containers. Okay, so pressure is directly related to, directly proportional to the number of moles. We just conclude on the first question there, first statement there, we have more nitrogen molecules, a higher number of moles of nitrogen molecules than argon, so the pressure is going to be higher for nitrogen. So this is the false statement. So that's what we're trying to get. When we give you a scenario there, we need you to be able to analyze the situation based on what we have already known, and we try to figure out a relationship between the two quantities there so that we can draw a conclusion. The third statement there says argon atoms have a greater average speed than nitrogen molecule. Well, at the same temperature, we mentioned same temperature, molecules, heavier molecules will move slower. Atoms of argon, 39.9 grams per mole. Molecules of nitrogen, 28 grams per mole. So lighter molecules will move faster. So in this case, particles do not all move at the same speed, but they all have the same kinetic energy. So higher temperature means higher speed, higher molar mass means lower speed. So that's what we conclude here. So this, in this case, argon has a higher molar mass. It cannot have a higher velocity there. Well, that's a false statement there. And then the last question there says the molecules of nitrogen collide more frequently with the moles of flask than the atoms of argon. Now that's a true statement. If you have two people in this room, having them two kids running around versus 20 kids running around, well, those 20 kids running around in the same room will have a higher chance of bouncing into one another. So this is a true statement there. Okay, so this is what we want you to be able to get at. And looking at the postulations that we have in kinetic molecular theory, we need you to be able to answer questions like this. So in order to answer questions like this, you have to know those assumptions. You have to know those postulations there. So that's something that we want you to pay attention to. Yeah, and the next two learning objectives, we are going to introduce more calculations involving the motion of the gas molecule. However, I do have homework questions assigned in the next two learning objectives there, but I will not test you on these. For the in-class exam there, I will not test you on these two topics there. But it's something that's fairly important because when you deal with gas molecules there, you need to know how fast they're moving and what governs their motion. So learning objective number 5 looks at the motion of the molecules there in relation to their mass, molar mass, and in relation to the temperature there. Okay. So the Graham's law, we need you to be able to use the Graham's law to solve problems involving diffusion and fusion. We'll give you the definition of diffusion and fusion in just a moment. And then the next learning objective, the last learning objective there, we are going to look into the assumptions that we made about the ideal gas law. There's no interaction between the gas molecules. Well, if you change the condition so drastically, with a very high temperature or very low pressure, or very high pressure, very low temperature there, the molecules are getting closer to one another, and you have to take into consideration about how they interact. So we're going to make corrections. Okay, so let's look at the diffusion and diffusion process. This is an example, an experiment that you can do about the diffusion. If you have a small container with some iodine gas or bromine gas trapped inside the flask there, okay, you put that smaller container into a larger container. If you open the lid of the smaller container and you keep the larger container capped, over time, you will see the molecules actually, bromine or iodine, they have a brownish color, yellowish color. So you will see the gases are starting to move out of the small container. Eventually, they will fill the entire large container uniformly, form a homogeneous mixture there. Okay? They will occupy the entire volume of the larger container if you give it long enough time. So diffusion is the process of gas migration due to the random motion of molecules. And that, again, ties back to the kinetic molecular theory. Gas molecules are always in random constant motion. So they're colliding with one another, they're colliding with walls there, and if you have an opening here, after the collision there, they're changing the direction of the, going up to the opposite direction. So the molecules will bounce out of the container. Eventually, you have a larger container there. Eventually, molecules will fill up the entire container there. So it is the diffusion that results in gas completely filling the container, forming a homogeneous mixture there. And that's the reason why when you bring a freshly baked pizza, 5 minutes, when you open the box, 5 minutes into that process, everybody in the room will smell pizza. It's a diffusion process. Okay? And we can actually quantify the speed of the motion by looking at the relationship between the speed of motion and the molar mass there. Okay? So if you have a U-shaped tube, and again, we can't call it U-tube now, and it's a U-shaped tube, I'll still call it U-tube. And if you mix two different gases together from either end, or from each end, how fast do those molecules move? Well, we can actually have ammonia gas on one side, hydrogen chloride gas on the other. Now here, the reaction here is that when these two gases meet with one another, they form an ionic compound, ammonium chloride. Ammonium chloride ion compound. All ionic compounds are solid at room temperature. So the location where ammonium chloride is formed indicates if you put the gases in at the same time. Well, the location where the ammonium chloride is formed indicates who is moving faster. In this case, ammonium chloride. In this case, ammonia. The molar mass is 17 grams per mole. 14 for nitrogen, 3 times 1 for hydrogen. You add them together, 17. Okay, and then for hydrogen chloride, hydrogen is 1, chlorine 35, so 36. Hydrogen chloride is heavier than ammonia. The location where the ammonium chloride is formed is closer to the end of where you put the HCl in there. So this is an experiment that you can actually do in the laboratory. If you have two different gases there, put them into the U-tube on the same time from each end there. Then the location where the ionic compound ammonium chloride is formed is closer to the end where you have HCl, meaning HCl is moving slower to travel less distance compared to the ammonia gas there. So this agrees with the postulation that we made there. Gases at the same temperature have the same kinetic energy. The smaller